Let me present the screen. Okay. Starting the slideshow. Let's start it from beginning. So we are discussing discontinuous controllers. Okay. So it's contained. We discussed this controllers, process, okay, and terminology. We discussed different process characteristics. Okay, like this. These are the process characteristics that we discussed, and then control system parameters, subcontroller parameters, and control variable. All these characteristics we discussed in last lecture, right? And then we started with controller modes, discontinuous control modes, continuous control modes, composite control. In discontinuous control mode, we have three types: two position, multi position, and floating. Continuous control, we have proportional, integral, and derivative. And in composite control, we have proportional plus integral, PI, proportional plus derivative, PD, proportional plus integral plus derivative. Right? So we had already started with discontinuous control mode, I mean two position control, and last lecture we discussed two position control, right? Error greater than zero, error less than zero, what happens below set point and above set point. Okay? It means by neutral zone of the set point that we discussed. So what is neutral zone then? So this is we saw an example on neutral zone, then finding the neutral zone. We saw the oscillations of the two position controllers. Okay? That is the peculiar characteristics of two position controller, that the controller output continuously oscillates about the set point. Okay, unless and until it exceeds or drops below the set point, controller doesn't take any action. So there will be overshoots and undershoots. Have the advantages, where it is viewed. All this discussed in last lecture. Let's start then with multi-position control. So this is just an extension of two position control. In two position control, we have only two outputs, either 0 or 100%, right? So this creates some difficulties for in between outputs. You can't adjust a controller output to anything other than 0% or 100%. So it will be a discontinuous control only. It won't be a continuous control, but some of the steps are added between 0% and 100%. Like say we want the controller output be 50% for a particular type of, particular amount of error. So that step is added. Okay. So if the error is between this one and this one, some range exceeds this range, then the output should be 50%. And then if error exceeds that range, it should be 100%. Okay. So there will be three steps instead of 0% and 100%. 50% step is introduced in between. Okay. And such number of steps can be introduced actually. So multiplication control mode extends intermediate position. This is to reduce cycling behavior. The reason for this being there should not be oscillations, okay? Overshoots and undershoots. This is represented by P is equal to Pi, where I represents 1, 2, 3, 4 number of states that we want to add. But generally, as we go on increasing the number of states, the controller becomes more and more complicated, right? So the next stage, the final control elements like valves or motors, etc., should have those in between steps settings also, right? So generally, uh, the three-step controller is more popular, not more than that. Okay, so I represents number of steps to be added in between 0% and 100% if the error EP is greater than EI, like even E2, E4, right? So if EP is greater than EI, then the controller output P has certain uh, fixed value of PI, like 50%, 60%, 70%, and so on. Okay? As the error exceeds certain set limits, plus or minus EI, the controller output adjusts to reset value PI. Okay? So P is equal to PI for EP greater than absolute value of EI, or I is equal to 1 to. This is how the multi-position control expressed. Okay? How was the two position control expressed? You remember? Let's go to the expression. P is equal to 0% for EP less than 0, and P is equal to 100% for EP greater than 0. And what is the difference between this and this then? Now P is equal to PI. Okay? P is equal to P1 for EP greater than E1. P is equal to P2 for EP greater than E2. P is equal to P3 for EP greater than P3, and so on. Okay? So there are in between steps from 0 and P can be adjusted. PI can be adjusted 10%, 20%, 30%, 50%, 75%, and so on. Okay? So this is what multi-position. So as I said, three-position controller is more popular, wherein step of 50% is added between 0 and 100%. Okay? So EP is less than minus E1. This is minus E1. If it is minus E1, then P is 0, right? Minus E1 to E2, right? Minus E1 to E2, some value E2, then output is 50%, right? Whereas if it is greater than E2, output is 100%. Okay? So as long as the error is between E2 and E1, control output remains at 50%, right? If the error exceeds E1 or more, then output is 100%, right? If it is less than set point by minus E1 or more, control output is 0. Right? So this is what is the multi-position, or rather three-position. So this can be explained here with this figure. Okay. See, this figure was controller output versus error, right? Here, error versus time and controller output versus time. Okay, this was what was the y-axis here. Y-axis here was controller output. X-axis was percentage error, right? Error and controller output. These figures are different. Here, error versus time. This is the practical one. Okay, error. How the error is varying with respect to time when the process is going on, right? The process is running, and during that, some error is created, and that error with respect to time is varying like this. Okay? The error is continuous function of time as we see, but the controller output is discontinuous function of time, right? See, controller output versus time is a discontinuous one. And as we saw, applying this, right? Let me copy. Okay. With this, see, minus even to even, if it is between this range, right? If the error is between minus even to even, then output is 50%. This is set. Okay. Here, the output exceeds plus even, right? And then controller output changes to 100%. Okay. This shows the time lag because it won't change suddenly. There is process lag also, there is control lag also. You know, so due to control lag, the controller output changes slower than the instantaneous value, sudden value, right? So uh, at this point, as the error exceeds the neutral zone, it is greater than neutral zone, above neutral zone. Minus even to even is the neutral zone, and for this we have 50% output. So greater than even, it is 100% then, and again it enters minus even to even band, and in that case again the output will be 50% set. Okay, and this also takes some time due to controller lag, right? So it will be delayed by some time, right? And at this time, at this point of time, the error then drops below minus even, right? Drops below minus even. Then for this, whatever is the time for which the error remains below minus even, right? Below this band, then the controller output will be 0% with delay, and as soon as it enters minus even to plus even band, again the controller output will be 50%. So between 0 and 100%, a step is added with 50%, and for the range of error between minus even to even, for this range of error, we have set the output to be 50%. One of the thing to be noted here is that this is direct action. We have seen that there are two types of actions: direct action and reverse action. So error is more, the output is more, or output is increasing. This is direct action. For larger error or error in positive direction, if the controller output decreases instead of increasing, that is reverse action. So this figure refers to direct action, right? So this was the explanation of pre-position control. What is the advantage? So advantage will be the cycling will be reduced, oscillations will be reduced, okay? But simultaneously we must know that when we have a 50%, rather three settings, 0%, 50%, and 100% setting for the controller, likewise, we must have same settings for our final control element like valves or uh, motors or so. Okay, so final control element must also have these settings, right? So that accordingly, controller gives the signal to the final control element, and that will be uh, affected then to the process, okay, transferred to the process. Next is the floating mode control. Okay, so this is slightly a different concept than floating mode. Let's see what is it. What is done in floating mode control? The output of the control is not uniquely determined by the error. Okay, two position and three position or multi position control that we discussed just now. The output of the controller was decided by, fully decided, solely decided by the magnitude of the error, right? Here, some different concepts. If error is zero, the output does not change but remains wherever was when the error becomes. So it remains the previous value, right? Whatever is the value, it remains at that if the error becomes zero, rather in between that neutral zone, right? If the error is between neutral zone, the output will not change, but where was previously at the instant of entering into the neutral zone, it will stay at that value. Okay? Whenever error changes from 0, right, up or down, then the controller output again starts to change. If change is positive, the output will change, increase or decrease depending upon direct action or reverse action, right? So error changes from 0, the control output again starts to change. Okay? There are two types here. One is called as single speed and other is called as multiple speed. The speed refers to the rate of change of controller output. Okay? So we can decide for what value of error, what should be the rate of change of controller output. Okay? If you want fast action, we can choose the higher rate of the higher speed. Okay? So we can have different speeds for different steps rather or different errors. Okay, let's see what is single speed and multiple speed in floating mode. Okay, so what is the difference here? Here the output for error or within neutral zone, okay, cannot be predicted. Whatever is the previous value, it stays at that. Let's see how it can be explained. In this mode, the output of the controller changes at a fixed rate. Which one? Single speed floating mode. Okay? Single speed floating mode. Output, controller output changes at a fixed rate when error exceeds the neutral zone. It is given by C. dp by dt, rate of change of controller output, is a constant AF plus or minus. It can be increasing, it can be decreasing, right? Depending upon how we decide it. Okay. So for EP greater than delta EP. So that's the neutral zone, delta EP. Okay. So dp by dt is the rate of change of controller output time. Kf is the rate constant, percent per second, and delta EF, that is not shown actually. If we integrate this equation, what we get finally is P is equal to plus or minus Kf into T plus P of 0. Okay. So equation of the controller output we get it for dp by dt plus or minus Kf. The P of 0 is the controller output at T is equal to 0. T is equal to 0 is the instant where we are considering the output where enters the uh, neutral zone. Okay. This will be best explained by the figure. Okay. T, this is the rate dp by dt versus E percentage error. Okay. So this is the neutral zone from minus delta EP to plus delta EP. Okay. Here the output is 0, whereas it is minus k for less than minus delta EP and plus k rate. Okay. dp by dt is equal to plus or minus k. Na? So plus k for exceeding above the neutral zone and minus k for dropping below the minus neutral zone. Okay. So if it is exceeding neutral zone on upper side, the rate of change of controller output will be plus k, whereas if it is dropping below the neutral zone, that case the rate of change of controller output will be minus k. Rather, uh, for this figure, we'll explain as like in last example, floating mode. Okay, so the controller starts with P of 0, some 60%, 70%, and when the error, this is error versus time again, and controller output versus time. So error versus time, error is varying like this, and this one. Okay, so the error lies between the neutral zone minus delta EP to plus delta EP. the error lies between minus delta EP to plus delta EP, and in that case, it lies in neutral zone. So the previous value or the P of is equal to 0 value is P of 0. This is say 60%. So when the error is between minus delta EP to plus delta EP, P of 0 continues to have controller output continues to have value of P of 0, that is 60%. Okay. Here is the point or time where the error exceeds our neutral zone, minus delta EP to plus delta EP, right? So as it exceeds more than plus delta EP, okay, the controller output then decreases at a rate decided by K. Okay, this is corresponding to minus K. What do you think? Can you tell me whether this figure refers to direct action or reverse action? Can I have some answer? This figure, does it refer to direct action or reverse action? Compare this figure with the earlier one. This figure. Okay. What is the difference between this and this one? Okay. Is it referring to direct action or reverse action controller? What are the characteristics of direct action and reverse action? We have discussed this direct and reverse action, where see this one, error can be positive or negative. Okay. When the increasing value of error causes increase in controller output, it is direct action controller. Okay, as in liquid level control. Reverse action is opposite. Increase in error decreases the controller output, as in temperature control of the heater. Okay, so increasing error, increase in controller output, direct action. Increase in error, decrease in controller action, controller output is a reverse one. Okay, so coming to this figure again. Okay, so increase in error, right? Increase in error, increase in output. This is direct action, right? Whereas in this case, increase in error is decreasing the output. It's minus K, and the rate of decrease, rate of drop is minus K, right? So this slope is minus K, right? So increasing error, this is reverse acting controller, right? Once again, see, for error lying between the neutral zone minus EP to plus EP, it has previous value P of 0. It continues to have controller output will have continues to at P0, P of 0. And as the error changes and exceeds neutral zone, controller output starts decreasing decided by the rate plus K, dP by dt is equal to plus, rather minus K, right? Minus K, and continues to decrease up to the point where again the error enters this band, okay, this neutral zone. And as soon as it enters neutral zone, then this is the controller output value when the error enters the neutral zone, and it will continue with that value. Okay, in three position mode we have seen that when the controller output was within the band, within this band, okay, irrespective of when it is between this band, it was 50%. Again it enters, it is 50%. Again it enters, it is 50%. That we have set. Here, such predictable output will not be there, and that's why it is called as floating. Okay, Here it lies within the band and output is this. Here it again enters the band and it is output is this. Here it again enters the band and output is this. So we can't predict the output. So it takes the previous value whenever the error enters the neutral zone. That's why it is called as floating. Okay, so output is floating, and this is single speed. Okay, the rate is either plus minus k or here it is plus k. See, at this point again the error enters the neutral zone and output will remain same at wherever it was. Okay, and that it will continue at this point up to this point when it drops below the neutral zone. As soon as it drops below the neutral zone, the rate becomes plus k because it is reverse acting, drops below the neutral zone, and output starts increasing with a rate of dp by dt is equal to plus k, and will continue to increase until again the error enters the neutral zone. And as soon as it enters the neutral zone, further it will continue with that value. Okay, so that's why this is called as a floating control, right? We can't predict the value of the controller output with change of the error. Okay, when the error is between minus delta IP to plus delta IP, we can't predict the output, and it just floats. It just takes the value, previous value, and continues with it. So that's how this is single speed. So this rate of decrease is exactly equal to this rate of increase. So this is minus k and this is plus k. dp by dt is equal to minus k and plus k, right? So dp by dt is equal to, it is minus k here and is plus k here. Okay. So this is single speed. So let the controller be reverse acting. P decreases as dp exceeds the neutral zone. This corresponds to minus k. Then dp by dt is equal to minus k, and the controller starts at some output p of 0. Then the explanation I have done. Okay, at the time t1, error exceeds the neutral zone. Error exceeds the neutral zone here. Okay. The controller output decreases at a constant rate up to t2. Controller output from t1 to t2 decreases. Next, at t2, error again falls within the neutral zone and therefore p floats at the present value up to t3. Right? So this is floating up to t3. At t3, error falls below the lower limit of neutral zone and it causes controller output p to increase up to t4 then. It increases. This corresponds to plus k then. Okay. At t4, error again enters the neutral zone. Therefore, p floats at whatever value it has attained at t4. Okay. So it has attained this value and will continue or float with this value until again the error changes its value and either it exceeds plus delta IP or falls below minus delta. This is what is the single speed. It means that plus minus k and this is plus k, dp by dt. Speed matlab rate. Okay. Multiple speed. Okay. So here instead of having a constant k, right? dp by dt is equal to constant k. We introduce different rates for different values of errors, right? In this mode, there are several possible speeds. That is, rate at which the controller output changes. The expression for the rate is given by dp by dt is equal to plus or minus. There it was only k. It can be k1, plus or minus k1, plus or minus k2, plus or minus k3, where dp by dt is equal to plus or minus k1 for EP greater than E1, dp by dt is equal to plus or minus k2 for EP greater than E2, and so on. If the error exceeds EPI, then the speed k of I, right? And here it shows this is 0, this is plus k1 and minus k1, right? For the range between minus E1 to plus E1. Okay? If it is below minus E1 and up to minus E2, the rate is minus K1, plus E1 to plus E2, the rate is plus K. So plus K1 to minus K1 is one speed or one rate of change. Okay, this is decreasing rate, this is increasing rate. Whereas if the error is below minus E2 or greater than plus E2, then the rate of change will be plus K2 and minus K2. So this is multiple speed control. Okay, what changes in this is with respect to this figure. If I explain, then there will be additional step. So again, if the error goes above, okay, so delta error increases. This was about say E1. Again, if it goes above E2, then the rate of change, this would be rate of change or rate of decrease would be more, rather slope of this will be more dropping like this, right? Again, if it drops below E minus E2, the rate will be higher, than it, the slope will be something more like this. Drop lower, the slope will be higher like this one. So that's the meaning. We can have multiple speed floating control. Where these floating mode controls are used, it is generally used for flow control systems, pressure control systems, small capacities, having self-regulation. Self-regulation property that we have already seen what is a self-regulating system and what is non-self-regulating system. The self-regulating system is where the system has a property of adopting the new value of controlled variable, settle down to new value of controlled variable, like temperature, when the process load changes automatically without any control action. Okay, where this was the temperature control. Suppose the temperature, the level in the tank increases, liquid level in the tank in inlet in inlet flow increases, and that decreases the temperature. The system adopts the new temperature, decreased temperature, and without any control action, it stays like that. So this is self-regulating. Whereas liquid levels, tank level control system, inlet flow and outlet flow equal, there will be level will be same. But if inlet, outlet remaining the same, if inlet increases slightly, then the level of the tank increases, and it will overflow the tank. So this is non-regulating type system. So these are generally used for self-regulating type system with again small dead time or lag time, right? So flow control and pressure control systems. Okay. So now these were the discontinuous control modes. What are then? What are the discontinuous control modes? Let's go to discontinuous. We discussed two position control, multi-position, that is three position control, and floating mode. Floating mode, we have single speed and multiple speed. So these are all discontinuous, right? There was the controller output. In each case, see, in each case, whatever the figure you see, the controller output is not a continuous function of time, right? It's not a continuous function of time. It is intermittent. discontinuous function of time. Right? So it is discontinuous function of time, not continuous one. Here it is constant, suddenly changes, suddenly changes, suddenly changes, and so on. Right? The controller output. I am not talking of the error. Error may be the continuous function of time, but the controller output is not continuous function of time. Right? So it changes. Here, in all these types, continuous control modes, mainly in the system, this discontinuous control mode is not suitable, right? Where the accurate controls are required, where a more precise relation is required between controller output and the error. Okay? This discontinuous control cannot be used. We have to use the continuous control modes, right? Say there is a chemical process, there is a large vessel, and many or various types of chemicals are being uh, added to that vessel. Its temperature and pressure is maintained, and the process goes on, okay, for a particular time, and then the outlet valve is opened and the reaction fully occurs, and whatever are the compounds, whatever the resulting chemicals, they are taken out, the product is taken out. Okay. For this, a continuous monitoring of the flow of inlet chemicals, flow of outlet chemicals, temperature of that uh, mixture, then pressure of that mixture, everything has to be precisely controlled. Otherwise, the quality of the product will not be good, or otherwise, required chemical will not be formed at all after the reaction. Okay? So there has to be proportion. Okay? Suppose an alcohol is to be produced, okay? Ethyl alcohol. So suppose I don't know exact reaction, but ethane and some water is required, right? So ethane and water or some other chemical, they are taken into a vessel, and for a particular temperature and pressure and all other parameters are adjusted, and it forms an ethyl alcohol. Okay? So there should be proportion of how much ethane should be there, how much water should be there, how much other catalyst should be there at a particular temperature, at a particular pressure. Okay? Then only ethyl alcohol will be produced. So in such cases, if discontinuous control modes are used, that case the output will be oscillating. Controller output will be oscillating, and the temperature or pressure or even the flow, inlet flow of the chemical will not be accurately controlled, and then the quality of ethyl alcohol, rather the output chemical, okay, product will be ethyl alcohol or not, that we can't predict. Okay? Because the process was not properly operating. Okay? So such processes requires the continuous control modes. Okay? So what are the continuous control modes? Proportional, integral, and derivative control. Right. So let's discuss one by one. Proportional control. In this control mode, a linear relationship exists between output and error. Okay? As the error increases, controller output also increases. If the error decreases, controller output also decreases. Okay? Over some range of errors about the set point, each value of error has a unique value of controller output in one-to-one correspondence. That is the peculiarity, speciality of the proportional controller. We have been given certain range of error. Okay? Later we say that this is called as proportional band. Okay? 0% to 100% error. For a particular this error, each value of error has a particular control output. Whether the error is increasing, whether the error is decreasing. If it is at a particular value, at a particular magnitude, it has a fixed value of controller output. Say error is 2%. For 2% of error, controller output should be 20% of the full scale, right? So whether it is increasing error and it becomes 2%, output will be 20% only. If it is decreasing and error becomes 2%, then the controller output will be 20% only. So what it means is that each value of error has a unique value of controller output in one-to-one correspondence, right? 2% error, 20%, 3% error, 30% control output, and so on, right? So the mathematical expression for proportional control mode is controller output P is given by some constant Kp. Okay, it is called as proportional gain. Kp is called as proportional gain. Kp into Ep, Ep is the error, plus P0. P0 is the control output. Controller output with no error, right? When error is 0, for 0 error there is some output. Okay, this is called as P0. So P is equal to Kp into Ep plus P0. This is the mathematical expression for proportional control mode, right? Again, let's come to the direct action and reverse action in proportional controllers also. Okay, and like in discontinuous control mode, 2 position and 3 position routing control. Here also we have direct and reverse action. Here EP is expressed as the difference between set point and measurement R minus B. We know if the measured value is above set point, the error will be negative. Okay, is R, the set point, minus actual measured value. So if the measured value B is greater than the set point R, then error will be negative and output will decrease. Okay, the term Kp into Ep will be subtracted from. This will be subtracted from P0, right? If it is so, this is the reverse action then. Okay? Sorry, the expressions have been interchanged. Let's make a correction later. So this should be minus and this should be plus. Expression for direct action is P is equal to. This is expression for direct action and this is the expression for reverse action, right? So Kp into Ep will be subtracted from Po for reverse action and will be added to P0 for direct action. So please understand correction. This is direct action, so it is written as the reverse action. This is expression for direct action and this is expression for reverse action. Okay? So this is proportional control, direct and reverse action. So here the proportional control action is explained. Okay? There are two graphs actually in the same figure to explain the effect of controller gain Kp, right? Proportional gain rather, proportional gain Kp. Okay? This is gain G1 and this is gain G2. This is graph for gain G1. Kp is equal to G1 and Kp is G2, where G2 is less than G1. Okay? So this is the saturation 0 and 100%. Okay. And these are the responses. As the error, this is set point, this is the set point, positive error, and this is negative error. Okay. And this is the band, okay, the proportional band, what it is called as. So in this band only, we will have linear relationship between the controller output and the error. Okay. And the slope depends upon the gain, right? Proportional gain, AP. Okay. So if the gain G2 is less, we will have wide proportional band. That is, we can have larger range of errors for which there will be linear relationship between controller output and error. Otherwise, what will happen? Outside this range, outside the range, what will happen? The output is saturated, right? 0% and 100%. What are the extreme cases? If we keep infinite gain, this is smaller gain, this is larger gain. Again, if I increase the slope, will be again higher. And what is the maximum slope? Infinite. Vertical line will have infinite slope. And in that case, what is the result? The result will be this angle will be 90 degrees and this angle will be 90 degrees. So proportional controller will take the form of two position controllers. Okay? So but we can say that the proportional controller with infinite gain becomes a two position controller, right? So here the gain is not infinite. Gain G2 is less. So for this range of error, this point, this set point, so below set point up to this and above set point up to this. If the error lies between this range or this band, then there is linear relationship between controller output and error. Okay, this is called as proportional band. Right? And this is the response where controller rather this gain KP or G1, and this is for G2. So as the gain increases, the controller output will be more. Say for this one, output here, this, whereas for the same output is more. Okay? So for this much value of error, if the gain is G2, output will be this much. Whereas for the same error, if the gain is increased to G1, then output will be 100%. You understand this? This is the value of error below set point, right? And if the gain is G1, output will be less than 100%. Whereas for this error, the gain is increased to G1, output will be 100%. Same is the case with this. Okay? For this error, this much error, output with G1 is 100%, whereas output will not be 100% in this case. Rather, 0. In this case, it will not be 0, right? So, as the gain increases, the controller output for a particular value of error will be more. But what is the negative effect of this? It decreases, increase in gain decreases the band or range of error for which the linear relationship exists. Otherwise, higher and higher the gain, band will be shorter and shorter, smaller and smaller, and the saturation will occur earlier and earlier. Right? So this becomes a narrow band as the gain increases. It becomes wider band if the gain is smaller. Okay, so we can decide the gain. We can let's choose the value of KP. Okay. In above figure, PO is set to 50% and two games. P0 is 50% of QG, and this is for gain G1 and this is for gain G. Okay. High gain correspond to large output but narrow error band within which output is not saturated. The range of error, this definition is very important. Definition is very important, right? The range of error to cover 0% to 100% controller output. Range of error to cover 0% to 100% of controller output is called a proportional band. And what is the formula for proportional band? Proportional band is defined by 100 upon Kp. Pb is given by 100 upon Kp. Okay. What is Kp? Kp is this. Kp into Ep plus Po. So this is Kp then. Kp is the proportional gain. So 100 upon Kp. Remember this formula we'll be using in the numericals, right? So the one-to-one correspondence between controller output and error exists in proportional band only. If the error is out of proportional band, then there will not be one-to-one correspondence. That is, linear relationship doesn't exist between controller output and the error. So today we'll stop here. Proportional control, then integral, derivative, and the composite mode controls, and some numerical based on this, because in exam also there are numerical problems on controllers, so we will solve those problems also. Let's stop here today. Okay. So what we discussed today, we started with floating mode control today, right? The three position mode, multi-position mode control today. And we discussed floating mode control, single speed and multiple speed, right? Then its applications, and then we started with control modes, right? Then proportional control mode we discussed today, the integral and derivative and all others that we will explain. Let me mark the attendance. Yes, the attendance is marked. We'll stop here today. Okay. I'm circulating. I'll be circulating Google form today. Can you hear me? Please answer anyone. I'm circulating Google form, and that is related to the higher education exams. Okay. Those who have filled up GATE examination form, registered for GATE, okay, they will write the GATE and will okay. And others who are interested in MBA, CAT examination, CET examination, and those who are opting for higher education abroad, that is GRE, TOEFL, IELTS. So these options will be there. Depending upon your interest, you select the choice and let me categorize who are interested in what. Okay, I want to know this data, so I'll be circulating the Google form for this one. Okay, please fill up and respond it. Okay, so let me end up the meeting. Thank you very much. Then, okay, I'm ending the meeting. Then, thank you.